Hello everyone. So today we're going to continue on our discussion on 4.1. So today we're going to start on talk about what 4.1 is really want to focus on, which is functions of one variables. Now, of course, you're probably thinking like, well, haven't we learned about function of one single variables already? And you're correct. Last year in BC Calculus, that's pretty much what you have learned. But last year when you learn about it in BC Calculus, you're learning about function of a single independent variable, but also a single dependent variable. What we go talk about this year is this type of function. Let f be a function that met from R to Rm. So therefore, in this case, f is a vector value function of a single variable. So different than last year is that last year the function that you learned have only one dependent variable. Now we talk about functions that have m that many dependent variable, but with only one single independent variable. So what do these type of functions look like? This is a function we usually call it f of t, and it would be defined by a list of coordinate function f1 of t, f2 of t, dot 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 to f sub m of t. So therefore, this type of function, vector value function of single variable, is actually defined by f. F is defined by m coordinate functions. Now, why do we start with these type of functions? It's because of a very simple concept. Notice that this function f is actually defined by m, the main coordinate function. But if you think about it, each coordinate function, let's say f sub k, is the kth coordinate function of f. What's important about it is that f sub k is actually a function that met from R to R. So what does that mean is that this is a real valued, real valued function of a single variable. Now, what's special about this type of function is that you actually have learned a lot about this type of function because that's what you learned back in BC Calculus. So essentially, what does that mean is that when I'm dealing with function of a single variable, but if it's vector value, all I have to do is basically take my knowledge of single variable real value function and just apply it to each one of these coordinate function to try to understand what happened to this function f. Now, however, I do want to mention this first now, and you probably hear me say this all the time. We are learning some very abstract math, and you need to have an understanding as to what we are actually trying to accomplish here, or what some of these things actually kind of represent. So when we have a function f that maps from R to Rm, this vector value function of a single variable, what does it represent? Well, very important is to understand this. F that maps from R to Rm always represent a curve in Rm. So this represents a curve in Rm. Now, as a matter of fact, you shouldn't be surprised. So here, the reason why I represent a curve, because we have only one single independent variable, therefore indicate that we are defining something that has only one dimension. Okay, here interesting thing to note is that the t is our input. As a matter of fact, in this case, we are going to be representing a curve in Rm in parametric representation. And as a matter of fact, you have seen this kind of function already. You just didn't realize that's what you got. And show you. Okay, show you an example. An example would be something like this. Let's say function f of t equal to t plus 2, 3t minus 1, 2t plus 1. That is a function f that maps from R1 to R3. So therefore, it represents a curve in R3. Now, you actually have seen this function before. Well, not the exact function, but this type of function before. And if you did not recognize it, then I can show you. But if you recognize it, that's a good job. So you probably didn't recognize this because it's not written the way that we normally write it when we first learn about it in chapter 1. So I'm going to write it this way. I'm going to go ahead and take this and rewrite it as f of t, which is equal to t plus 2, 3t minus 1, 2t plus 1. Which then I can separate and then I can pull out the t. This is a parametric representation of a line in R3. A line is a one-dimensional object, so it's a curve. And the reason why these both have one single parameter. Okay, now of course, if we have a curve, then it would not be able to written in this way because we won't be able to factor out this vector right here to indicate the direction. But what you have been learning in chapter 1 about lines in parametric form, that is actually a function of this type, a function that maps from R1 to Rm. Okay. Interesting. But at that time, when I show you the parametric representation of a line, I cannot really explain to you using function notation. That's the problem. So notice that when you write a parametric curve, that's kind of what you define it into a function notation. Okay? And that kind of identifies a function that maps from R1 to R3. Now, some of you might already thinking about, well, then what happened to the parametric representation of a plane? Now, we get to those later. But just not right now. Remember, I cannot show you everything that you need to know. Okay, so we get to those toward the end of chapter 4. Now, the really powerful things about talking about this type of function is defining a vector value function through coordinate function. Like in this case, I have the 3 basic coordinate function. I have, in this example right here, I basically have this to be x, this to be y, and this to be z. So if you want to think about it, this is x, this is y, this is z. So therefore, implying that f of t equal to t plus 2, 3t minus 1, 2t plus 1. It can be written as this. And it can also be interpreted as this. F of 1 of t, f sub 1 of t is t plus 2. F sub 2 of t is 3t minus 1. And f sub 3 of t is 2t plus 1. So that would be me listing out the 3 different coordinate functions that make up of this function f. Now, if I define this to be in R3, then I can also define x equal to t plus 2, y equal to 3t minus 1, and z equal to 2t plus 1. Some cases you might write that as x of t, you might write this as y of t, you might write this as z of t. But sometimes you just simply write x, y, z instead. Now, is there a functional difference between writing x versus x of t? Mathematically speaking, not really, but it's a matter of interpretation. If you write x equal to t plus 2, you're basically saying that the dependent variable x is equal to t plus 2. If you write x of t equal to t plus 2, then you're basically defining the function x is defined to be t plus 2. Slight different, but not that big of a deal if you write x or x of t. Personally, x of t is nicer because it defines the independent variable. Sometimes it's left to for you to interpret or think about, so sometimes it could create confusion. But also in the same time, writing t x equal to t plus 2 require writing 3 less things, so that's definitely a plus. Remember, mathematicians hate to write. All right. Now, one of the most powerful thing about defining a vector value function using coordinate function is that because I can now just kind of put all the coordinate function together to form this vector value function, and vice versa. So meaning that when I now define something new about this type of functions, I can actually just make use of the definition that I already know on each coordinate function and then use that to imply what's happening to the vector value function. What do I mean by that? Well, let's talk about some concept that you have learned. How about limits? Suppose we're given, so here's a definition of how limits work. Suppose I'm given a function f that maps from R to Rm. Let's say in this case, function f of t is equal to f1 of t, f2 of t, to f sub m of t. This is how we go define limits. Then the limit as t approaches some number t sub 0, f of t, exists if and only if the limit exists for all its coordinate function. What does that mean? Meaning the following. Limit t approaches t sub 0, f of t exists if limit as t approaches t sub 0, f1 of t exists, limit as t approaches t sub 0, f of 2 t exists, and then continue on to limit t approaches t sub 0, f sub m of t exists. So if all of these exist, then this exists. So therefore, implying that if I want to find a limit of a vector value function of single variable, all I need to know is how to find the limits for each of its coordinate function. And the beauty of this is that the coordinate function is a real value function, which means these are the type of function that you have learned already in BC calculus. And you know what to do. So essentially what does that do is that it turns a single limit problem on a vector value function into multiple limit problem for a real value function. And so therefore it doesn't make it more difficult, it just makes it more time consuming because you have to do more of them. Now I'll give you a very simple example. Let's show you. Suppose I have this. Let's say f of t is equal to t radical t 1 over t. And what I'm going to do is I'm going to ask you to find me the limit as t approaches 4 f of t. So now the way to do that is simple. Because I have a limit on a vector value function, and this vector value function has 3 individual coordinate functions in it. So in this case, this is our f1 of t, which is just t. This is our f sub 2 of t, which is radical t. And this is our f sub 3 of t, which is 1 over t. So if I want to find the limit as t approaches 4 f of t, all I have to do is to simply do the limits for each of this coordinate function and then see if they all exist. And if they all exist, then we are good to go. So therefore, meaning the following, if I want to take the limit as t approaches 4 f of t, that basically means it's the limit as t approaches 4 of t, f1. Limit as t approaches 4 radical t, that's f2. And limit as t approaches 4 1 over t, that's f3. And so now I just have to evaluate each one of these individually. So this would be pretty easy to do. If you recall from basic calculus, when you evaluate limits, all you really do is plug in the number and hope for the best. And unless there's something crazy happen, you can just say, well, if I get a number, that's my answer. So if I do that, I'm going to plug in 4. I get 4 for the first limit. I get 2 for the second limit. I get 1 over for the last limit. And since none of these actually present an issue, this is my answer right there. Plain and simple. Now, to give you a counter example, what happened if this? So I'm going to go and call this, let's say, A, for instance. So now what happened is, what if I ask for, let's say, B? What if I ask for this? Let's say I want to find out what happened to the limit as t approaches 0. And so we probably already noticed what's the issue here. So, but let's go through this and see. So let's say t approaches 0, f of t. So that would mean it's the limit as t approaches 0 of t, limit as t approaches 0, radical t, and limit as t approaches 0, 1 over t. Now, notice that when t approaches 0, t approaches 0. If t approaches 0, radical t also approaches 0. But now here comes the big problem. This one right here does not exist because 1 over 0 does not exist. Okay? Then, so what happened to this whole thing? This whole thing failed to exist. Because in order for you to have an answer for this limit, all 3 of these must define. If any one of them does not exist or equal to positive or negative infinity, then this whole thing would not exist. The reason why, because we cannot define a vector, in this case in R3, with one of the coordinates not being defined. Whether it's go to infinity or does not exist, it would mean that we cannot define an actual number for one of the coordinates. And when that happens, I can't define the entire vector. Alright? So pretty straightforward. So if you remember how to do limit problem from last year, then you have no issue because it's basically just doing that. But instead of like asking you to do, I don't know, 10 limit problems, I can now just give you a single limit problem, but it's a single limit problem in R10. Then now you have to do 10 single limits, just like I will ask you to do 10 problems. All right. So the next thing we're going to want to talk about is the following, so which you probably suspect this is what we're going to talk about, because if you simply just think about what happened in BC calculus, it will make sense. The next thing we're going to want to talk about is called continuity. Now, we're actually not going to talk too much about continuity, but simply just going to define it, because we're going to mainly just deal with continuous function for us in this class. So most likely every time when we're doing a problem, I would basically tell you that the function is continuous. So therefore, it's not as big of a deal, but I do want to define continuity. So how do you define continuity in this case? Well, actually define the same way as limits. Let's say given a function f that maps from R to Rm. So in this case, meaning that function f of t is equal to, once again, f1 of t, f2 of t, to f sub m of t. We're going to define the following. F of t is continuous at a point t sub 0 if this is true. If f sub k at t sub 0 is always equal to limit as t approaches t sub 0, f sub k of t. For all coordinate functions, oops, wrong word. For all coordinate function, f sub k of t. So therefore, basically what does it mean is that in order for a vector value single variable function to be continuous, it implies that all the coordinate function must be continuous. Which makes sense, because if any one of the any one of the coordinate functions is not continuous, then that would mean that now you have a gap in one of the coordinates. And therefore now the entire vector cannot be defined at that one point. So that would make it not continuous. Okay, now hopefully some of you remember this condition right here. That is the continuity condition that you remember learning in BC calculus. See, some of these things that you learned last year, now it all come into play. Now the next one is probably the most important one that we have to talk about, and that would be derivatives. So what would be the derivative when you take a vector value function, single variable, and find the derivatives? Well, I shall show you. So let's say given a function f that maps from R to Rm. And once again, the function f is f of t equal to f1 of t, f2 of t, to f sub m of t. The derivative of the function derivative of f, which is called derivative of f of t, which is called f prime of t, is defined to be this. F prime of t is equal to f sub 1 prime of t, f sub 2 prime of t, to f sub m prime of t. So essentially, meaning that the derivative of a vector value single variable function is simply just basically taking the derivative of each of the coordinate function. So this basically implies that the derivative of f of t is basically the vector of all the derivatives of its coordinate functions. Now I do have to talk about something important called differentiability, meaning whether derivative exists. So this is the terminology that we would say. F of t is considered to be differentiable, meaning its derivative exists, differentiable at t equal to t sub 0, if and only if this is true, if and only if all its coordinate functions are differentiable at t equal to t sub 0. Now, what do I mean by all that? So, well, how about let's give you an example to illustrate. Suppose we have the same function that we just saw before, t radical t 1 over t. Let's say we let f of t equal to t radical t 1 over t. Now, that would mean that this function f maps from R1 to R3. Okay? And also, what does it mean is this? Mean f represent a curve in R3 in parametric representation. And that would imply that t is our parameter. And then we have three coordinates or three variables, we can simply call them x, y, and z. Good. So meaning in this case, f of t equal to t radical t 1 over t implied that we have x equal to t, y equal to radical t, and z equal to 1 over t. Okay, in this scenario, t is a parameter, and then x, y, z are the variables, which in this case, technically speaking, they are the dependent variables, and our t is the parameter, which is the independent variable. Okay, so now if I look at this right here, I can now talk about what is the derivative of this thing. Okay, so what is the derivative of this thing? So I can now define f prime of t. F prime of t would equal to 1 over 2 radical t, negative 1 over t squared. So that would be the derivative of radical t and 1 over t. And if you do not remember how to take the derivative, you have to make sure you go home, make sure you study, and make sure you dig up your note from BC Calculus, because I am not going to be able to reteach you everything about finding derivatives and things like that. You learned about that last year. You spent almost entire first half of the year learning about that. So I'm not going to be able to tell you that. Now, notice that this expression right here, if t equal to 0, then this thing would not exist. So therefore, we can say that f prime of t is not differentiable at t equal to 0. Why? Because f prime of 0 would equal to 1 over 2 radical 0, negative 1 over 0 squared. And so notice that these two things does not exist. Now, some of you might also already notice something important about this and realize that, oh, of course, f prime, or actually I should say f, I'm sorry. F is not differentiable at t equal to 0. Because you notice that f is actually not continuous at 0. Because f is not defined at t equal to 0 because of the 1 over t. So therefore, you probably remember learning it last year in BC Calculus. When a function is not continuous at a specific point, it cannot be differentiable at that point. Okay? Now, I know right now is about 27 or 28 minutes, so I just want to show you one more thing, and then that will be it for today. In this expression right here, we define what we call the prime notation. So this is usually referred to as the prime notation. The prime notation basically would define that you have a function f of t, then its derivative is called f prime of t. So that's why I call prime notation. Prime. Okay? Now, however, you might define one of these functions because it is a vector output. So therefore, you could define this type of function using what we call vector notation. And when that's the case, we're basically meaning that we define vector x to be equal to f of t. And therefore imply that we can now refer to as vector x of t as the function f of t. And when we do that, we call vector x of t x sub 1 of t, x sub 2 of t, ... to x sub m of t. So this, technically speaking, mirror what we usually call vector x, which is x1, x2, ... to xn or m, doesn't matter what I use as a last number. But here, instead of defining vector x to be a set of numbers, x1 is a number, x2 is a number, xm is a number, now we're going to define x1 not as a number, but as a function that gives out a number. And the x2 being another function that gives out different numbers, and then all the way to xm. Now, the reason why I will point this out, because in this notation called vector notation, the derivative use something called the over dot notation. for derivatives. This notation is usually used in physics, where when you have vector x of t, its derivatives is called vector x over dot of t. And this single dot on top indicated this, this is a first derivative because they have one single dot on top. And yes, you guess it. What happened if I want to find second derivative? Second derivative, its second derivative is called this, with two dots on top. And that represents second derivative. So instead of using 2 prime, you now use 2 dot. Now then you're probably thinking like, what happened if it's third derivative? Well, guess what? I did mention that this notation is more commonly used in physics. And in physics, you really don't care about anything higher than second derivative. And I'll explain to you why, not today, but tomorrow. Alright, so I think we're going to stop right here for today. We're going to continue some more in the next video. Alright, talk to you guys later. Bye-bye.